Alright, so today I'm going to be explaining another important article with the title Modularity-based sparse soft graph clustering. So this paper in 2019 by Indria. Indria is a great research center in France that they do work on machine learning, AI, and it's very good, just like Max Planck in Germany. Clustering is a central problem in machine learning for which graph-based approaches have proven their efficiency. In this paper, we study a relaxation of the modularity maximization problem well known in the graph partitioning literature. A solution of this relaxation gives to each element of the dataset a probability to belong to a given cluster, whereas a solution of the standard modularity problem is a partition. We introduce an efficient optimization algorithm to solve this relaxation that is both memory efficient and local. Furthermore, we prove that our method includes as a special case the Louvain optimization scheme, a state-of-the-art technique to solve traditional modularity problem. So we had discussed different papers about modularity, and you know that for a given node partition, modularity is defined like Q. That is just the difference between the probability to pick an edge between two nodes of the same cluster. For example, intra-cluster edge, and the probability to pick such an intra-cluster edge in a random graph generated with the so-called null model. So clustering approaches based on modularity try to solve the modularity maximization problem. And so there are many variations of that, but relaxations of hard modularity have been tackled by a few papers. They all introduce membership matrices P. So these relaxations have similar forms and are very close to the one that we talked. And for example, this reference uses softmax parameterization. But the main limitations of these methods lies in the maximum number of clusters that must be specified. We could get around this issue by taking large values for k, but all the approaches cited above do not scale well to large k. Indeed, the solutions found by these methods are dense matrices. So this paper focuses on soft modularity. So everything is the same now. They have membership matrix P, and the sum of them is equal to 1. We define this membership matrix that given a matrix P, we use P sub I to denote the vector that corresponds to the ith line of P, and P sub K to denote the vector that corresponds to its kth column. We introduce a natural relaxation of the problem where coefficients of P can take real values. If P is a feasible solution of this problem, then P sub ik can be interpreted as a probability. It corresponds to the probability for a node I to belong to cluster K. So by solving this relaxation of the modularity optimization, we can obtain nodes that belong to multiple clusters, unlike in the classical modularity maximization problem. We can rewrite the relaxation of modularity optimization as a classic minimization. So the soft modularity objective function is non-decreasing, as is shown if the step size satisfies this condition. And they have proved it. Also, I should talk about this local gradient descent that the update of theorem 4.3, this is a kind of update, right? And this update relative to node I can be decomposed into just two steps. At the first step, it seems to depend on information from nodes of V and to require the computation of a sum over n terms. However, the gradient descent step can be written like this, where P bar, this one is a weighted average of vector. The vector P bar can be stored and updated throughout the algorithm. Then the computation of P hat is purely local in the sense that it only requires information from neighbors of node I. Moreover, the sum to compute contains only these sub-I terms. So the cluster membership variable P is a n by n matrix. The memory cost is order of n squared. Now the classic algorithm to perform the projection onto Y is described in this reference. First, it starts by sorting the vector into mu i's. Then it finds the maximum of this term and defines theta so that pi of y, pi satisfies this relationship. This algorithm runs in order of n log n because of the sorting step. Finally, the algorithm can be described like this. First, we do initialization, then one epoch for each node I. We go through all k's. For any k, we update it, project it, and then update it. One epoch of the algorithm is typically repeated until the increase of modularity falls below a given threshold, as in the Louvain. This is a very popular algorithm. And they also discussed with this popular algorithm, the link with this popular algorithm called Louvain algorithm. So if the learning rate T is larger than a graph-specific threshold, one update performed by our algorithm reduces to a local update performed by the Louvain algorithm. First, we observe that if the membership matrix P verifies, then the update rule is this relation. So this is the hypothesis. It's a non-binding in real cases because if the weights are continuously distributed, then we will have this hypothesis with probability 1. Also, they have this proposition that says if P is a membership matrix, if the hypothesis is verified, then the update rule reduces to this one if K is such. And C sub K denotes the case cluster defined by P. And you see algorithm performance in the function of cluster size and the overlapping stochastic block model. This is a very classic approach by some mathematicians. Now we talk about it in the context of computer science, community detection, and yes, it is in now we use it in even in hierarchical graph pooling. So these are the experimental results. They just did it for synthetic data. The Wikipedia, and these are real data. OpenFly's Wikipedia, Snap data sets. For example, a font score for different data sets. also their execution time.